to know just one of them for multi-surface heat transfer. And that is the powerfulness of what you're doing here. But this is all under the umbrella that the surfaces are diffuse. Okay, that's something to keep in mind. Which is why we went into Kirchhoff's law to say that, okay, if a surface is diffuse, what's the upshot? The absorptivity on a spectral level is the same as the emissivity on a spectral level. So what are we going to do with all this information? Okay, so this is called the know one, know all rule. And so it is not as painful as I portray it to be, you just need to know one. And that can be calculated by using tables where they have experimentally calculated these values using the geometry, okay, of the surfaces. So what we are going to do is we are going to make use of all of this information. The main thing that I'm going to take away from here today is the two things. Fij Ai is Fji Aj summation Fij over j is equal to 1. I'm going to take these two equations and we are going to create a radiative resistance network which is different from the resistance networks we've done for conduction and convection. Conduction and convection, if you look at conduction in the absence of heat generation and so on, there is a nice linear relationship between the temperature change and the heat flux. Don't use that same idea here. This is a different idea, but you will see a lot of similarities. So our aim now, how to construct a resistance network for multi-surface interactions, obviously in radiation. Okay, so here is how we do it. I'm going to set it up. I have 5 more minutes left. We consider the same. Okay, we consider the same 3-surface enclosure. I'm going to look at the net radiant energy that is emitted by surface 1. This is not the net radiant energy leaving surface 1. This is emitted by surface 1, which means that this is the net radiant energy which includes the emissive flux from surface 1 and the irradiation on surface 1. Okay, so this is going to be E1 alpha 1 G1. Okay, this is the net radiated flux. I guess multiplied with the area, so net radiant energy. Energy rate in watts from surface 1. If I assume that the surface is diffuse and gray, which is the most restrictive form of Kirchhoff's law, and that's what we're going to invoke today. Which means that all of the epsilons is equal to all of the alphas. So I'm going to substitute for alpha 1 in terms of epsilon 1, and instead of writing E1, I'm going to write it as epsilon 1 times the emissive power of an ideal body at temperature of the surface 1. So Q1 is now epsilon 1 EB at the temperature T1 minus epsilon 1 G1 multiplied by the area A1. Okay? So this is equation 1. I'm going to invoke the definition of radiosity. Look at that there. So J 1, the first equation written there in that panel, is E1 plus rho 1 times G1. But reflectivity is 1 minus absorptivity, so this is alpha 1 times G1. But alpha 1 is the same as epsilon 1 because it's a diffuse gray surface, so that J1 is E1 1 minus epsilon 1 G1. Or G1 is written in terms of J1 and E1, but instead of E1 I can write epsilon 1 times EB at temperature T1, so I can say that G1 is J1 minus epsilon 1 EB at temperature T1, all of this divided by 1 minus epsilon 1. This is the equation 2. I'm going to compare equation 1 and equation 2. Wherever I have a G1, I'm going to do the substitution. Okay, so substitute into equation 1. You see the fractions have not come into play. They will, don't worry. So Q1 is now A1 epsilon 1 EB at T1. Just rewriting stuff. Instead of G1, I'm going to substitute this chunk here. So that's going to be minus epsilon 1 J1 minus epsilon 1 EB by 1 minus epsilon 1. And big brackets close. Looks complicated, but I'm going to take a common denominator. I'm not going to show the steps. This is what I'll end up getting. So take a common denominator of 1 minus epsilon 1, go through the weeds, and then you get the following. Q1 is A1, 1 minus epsilon 1, and this is epsilon 1 EB at T1 minus J1. This is what you'll end up getting. This is very simple looking now, and it's going to be much more simpler when I write it in the following form. Q1 is EB T1 minus J1 divided by 1 minus epsilon 1 by A1 epsilon 1. Now this looks something like a temperature difference divided by the resistance is equal to the current flowing through the circuit. Doesn't it look like that? It absolutely does, whether you believe it or not. And this is called as the surface radiative resistance. And what we will show, very last second, is that I can have another equation which is going to be exactly similar to it, but with all the fractions coming into play, and I can then draw a radiative resistance network. It will look something of the following sort for the three surface enclosure. Where all of the foundational nodes will be the emissive power of an ideal body at temperatures T1, T2 and T3. All of these inner nodes will be J1, J2 and J3. The inner resistances will be coming from the fractions. The outer resistances will be coming from the surface areas. And this is what we are going to do in the next class. And my thinking is I'm not going to hold the review on Wednesday. I want to save that class for doing actual stuff. I will hold the review on Tuesday. Okay? And I'm going to go through the radiative resistance network. If at all you want to learn anything in radiative heat transfer, this is the thing. Thank you.